So if something happens like voice breakage or something like that in between, please feel free to message and ask me to uh, take care of that. Okay. All right. So we are actually we have started magnetism part on the in the last class, magnetism in matter. Okay, so here we'll be learning how in different types of materials how magnetism is created or magnetism arises, and we'll be learning what is earth magnetic field and maybe the probable reason for that, and how is that earth magnetic field is affecting things. Okay, those things we'll be learning here. Then we'll be learning here magnetostatics, Gauss's law for magnetism, which we have learned for electrostatics. We'll be learning for magnetism here. Okay, so today we'll start with this topic, the dipole in a uniform magnetic field. Look, this is magnet. This is a topic which I have already taught. Similar topics I have already taught you in case of electrostatics. These are similar to like this dipole. When you keep a magnetic dipole in a uniform magnetic field, situation will be similar to that case, that electrostatic case itself. Okay, so people who have attended the last class or missed the last class both, just for them, uh, quick recap that in the last class I have talked about bar magnet. So you have been learning this since your lower classes, like 8th standard onwards. You will be learning this bar magnet. So it has north and south pole, as you know, and it can see north pole. Similar poles will be attracting each other, sorry, repelling each other, and opposite poles or unlike poles will be attracting each other. And you look this figure, if you keep iron filings on a cardboard over a bar magnet, you can see this kind of pattern which actually represents the magnetic field line. And as you have learned in electric field lines in case of electrostatics, similar to that, very similar to that, magnetic field lines actually are the field lines or the arrowhead lines which are actually used to represent the magnetic field or the strength of the magnetic field, direction of the magnetic field. Okay, and in this case, only difference between electric and magnetic field is, this is the case of electric field. So electric field line, this figure, electric field line starts at positive charge and ends at negative charge. Okay, and for isolated charge particle, the electric field lines will be emanating from that charge particle and going to infinity. But in case of magnetic field, both the cases magnetic field, this one, these are two bar magnets. Look, this is north pole and this is south pole. So magnetic field lines are emanating or emerging from north pole and they're entering to the south pole. And in this case, you look the difference. The magnetic field lines are forming a closed loop, but in this case, electric field lines are not closing closed loop. Okay, not making any closed loop, but magnetic field lines are making closed loop. Okay, so this is the only difference, and there is a significance as well. I'll tell you today what is the significance of closed field lines and what is the what is the significance of field lines which is not closed. I'll tell you today. So this part, and then we had discussed that bar magnet can be compared to a solenoid. That's why the topic is bar magnet as an equivalent solenoid. Why? Because we have seen the magnetic field line similar to the similar to the bar magnet. So we know the magnetic field line for solenoid is very similar to the bar magnet. Magnetic field lines for bar magnet. So from that analogy, we can think of the solenoid to be compared to a bar magnet. And doing that, we know how to calculate the magnetic field for a loop. Okay, that we have learned in the previous chapter. For a current carrying loop, how we calculate magnetic field due to that particular loop at any point on the axis. So this is what, using this solenoid case, we can find out the magnetic field for a dipole, since we will be for a bar magnet, since we are comparing a bar magnet with solenoid. We can compare the magnetic field strength of solenoid at any point on the axis, or maybe equatorial point. I can calculate the magnetic field for solenoid, and that will be exactly equal to the magnetic field for a bar magnet. So that day we had already discussed, and with certain approximation we could show you that the magnetic field created by a solenoid or a bar magnet at any point on the axis is given by this: B is equal to mu 0 by 4 pi 2 m by r cube, which is very similar to the magnetic field created by an electric dipole at any point on the axis. Only difference is this one. So this factor is mu 0 by 4 pi here, which is analogous uh, to the factor 1 by 4 pi epsilon 0 for electrostatic. Okay. So up to here we had discussed last day. So today what we'll do, we'll see if we keep a dipole, magnetic dipole, in a uniform magnetic field, what happens to that. So with this, we can find out, with the help of this particular topic, we can find out the magnetic field, exact magnetic field for a bar magnet as well. So you might be thinking what I am talking without any writing. So since I had already taught you in the previous classes, those things I did not write. So the new things I'll be writing today, which is okay. So look, see, if I have a bar magnet like this is north pole and this is south pole. If you have been asked to calculate magnetic field at any point on the axis, so I have told you how to calculate just by comparing with solenoid. Even any point in the equatorial point here, suppose, you can just get the magnetic field just by comparing with electric dipole. Okay, so magnetic dipole and electric dipole, the magnetic field created by magnetic dipole and the electric field created by electric dipole on any axis is actually they are equivalent. Suppose in case of electric dipole, electric field was actually 2p by 4 pi epsilon naught r cube, and for the case of bar magnet, we have found out this is mu 0 by 4 pi, this is 2m by r cube, like that. Okay, so now the question is, if somebody asks you to, if somebody gives you a bar magnet like this, okay, like this, and ask you to find out magnetic field at any point, maybe here, maybe here, maybe here, maybe here, experimentally. Okay, then how can you find out magnetic field? Magnitude of the magnetic field. How can you find out magnitude of magnetic field created by this bar magnet at any point? So the answer to that is the topic today, that is dipole in a uniform magnetic field. I think it is not very much visible. I'll write here dipole in a uniform magnetic field. Okay, so I can do a simple experiment. What is this experiment? Look, the experiment, see, since I have a bar magnet and we know bar magnet creates magnetic field around it. Okay, obviously the neutral point, middle point will be neutral point where there is no magnetic field. Okay, so here B will be 0, but both sides N and S, they'll be having, they'll be creating certain magnetic field. Okay, so suppose I keep, so what is the experimental procedure to calculate magnetic field or the magnitude of the magnetic field for a bar magnet is that you have to take a bar magnet, place it, okay, place it nicely, and then take a compass needle. This is compass, okay. You need to know the magnetic moment of the compass needle. You need to know, see, this compass needle will be actually pivoted to some point like this. So it will be like this, pivoted, okay. So it is actually or that means it is supported by some small uh, support. So you need to know the rigidity modulus of this compass also. Sorry, I'm sorry. Moment of inertia, not rigidity modulus. Moment of inertia. Moment of inertia. Moment of inertia is actually equivalent to, this is denoted by I, capital I. Moment of inertia is denoted by capital I, and this is actually related to, this is moment of inertia is an inertia, moment of inertia. You might be knowing what is inertia from Newton's first law. Inertia and the mass is measure of inertia from Newton's first law. But then what is the moment of inertia? We know only inertia, measure of inertia is mass. Measure of inertia is mass. This is for linear motion, okay? This is for linear motion. And what I'm talking about actually is this for moment of inertia is for rotational motion. Rotational motion, it is for rotational motion, okay? Moment of inertia. So see, in this case, moment of inertia which is denoted by I, and mathematically the expression is actually m r square, okay? For a single particle, if there are many particles, so summation over m r square, okay? M I R I square. So mass into distance square from the axis of rotation, okay? Square of the distance, mass into square of the distance of that particular particle or any particle of the mass distribution from the center, from the axis of rotation. That is called mathematically moment of inertia, and this is actually the measure of inertia for rotational motion. This is measure of inertia in rotational motion. Inertia in rotational motion, okay, in rotational motion. So in linear motion, mass is the inertia, but in case of rotational motion, moment of inertia I is actually the inertia. So experimentally, if we want to calculate the magnetic field created by a bar magnet, what you have to do? You have to bring a compass needle near to the magnetic bar magnet, and you know what will happen in that case if you bring a bar magnet. Bar magnet acts as a dipole actually. sorry, if you bring a compass has both this N and S, north and south, so it can act as a dipole. Like your electric dipole, you have positive and negative charges. Okay, so in this case, north and south pole, as if they are together. Obviously, in case of magnetism, these poles, north and south pole, cannot be separated. We have discussed in the previous day. So, so this compass will be acting as a dipole, and since you are keeping this compass needle near to the bar magnet, the bar magnet will create a magnetic field, and the compass needle is now in that magnetic field created by. If that magnetic field is uniform magnetic field, B created by this. How to calculate this magnitude? What is the magnitude of this magnetic field? How to calculate this magnetic field created by this bar magnet? So you are bringing a compass needle which has magnetic moment known. You know the moment of inertia of that. Okay. If you know these two things, then things are all right. Let us see how we can calculate that. How we can calculate magnetic field. See, this compass needle is in uniform magnetic field. So what is the tendency of this compass needle? The north pole will be exactly in the direction of magnetic field. Okay, in the direction of the it will be like this. It will it will be like this. This is the direction of magnetic field. It wants to be in the direction. North pole wants to be in the direction of magnetic field direction, and south pole in the opposite direction of the magnetic field. So that means this north and south pole, they want to become parallel to the magnetic field. Now, if you just displace the north pole by an angle, certain angle theta from this magnetic field, look here as it is shown. I'll clean everything. So as it is clean, so it was in this direction. So it has been just displaced by theta degree angle from the magnetic field. So what will happen? So at this stage, as you know from the electrostatics, if you keep a dipole in a uniform magnetic field, it will experience a torque. So what is the torque? That is given by m cross b. Okay, or I can write mb sine theta. Okay, this is the angle theta. Theta is the angle between the dipole and the field. Here in this case, magnetic dipole and magnetic field. All right. So this is the torque. Okay. Now see, since I know magnetic moment of this compass needle and moment of inertia, then you know, like since it has a torque, like it is experiencing a magnetic torque m cross b or mb sine theta. So if you want to bring it back, actually, so this has actually a tendency to come back towards its original position, and for that, you know, you need a restoring torque. Restoring torque. What you need is restoring torque. Restoring torque. See, once you displace this, it will try to come back to its original position, this direction, and that will be done by restoring torque. What is the restoring torque and from where the restoring torque is arriving or arising? The restoring torque is arising due to the moment of inertia of this compass needle itself. Okay. So see, the restoring torque is actually due to this compass needle, and it has certain moment of inertia, and from there it is coming. So that I can write restoring torque, I can write as I into alpha. Alpha means what? Alpha is actually, so I is moment of inertia, alpha is angular acceleration. Angular acceleration. Okay, angular acceleration. So here what will happen, you know, once you just displace it, it will not just come back to here and stop here. It will actually oscillate back and forth in this angle. It will oscillate back and forth. Okay, oscillate back and forth. And if we can find out the time period for oscillation, actually experimentally we can do that. Time period means, see, if it starts from here, oscillation starts from here, go to the other end and come back to this end again. That is the whole time. The time it takes for that complete oscillation is called time period. So that we can find out from our observation, careful observation, and with stopwatch. Okay, the time period I can find out. See, mathematically, if we know the time period for this oscillation, and since my moment of inertia and magnetic moment of this compass needle is known, I can find out the strength of the magnetic field created by a bar magnet around the compass needle. We can find out that. Okay, we can find out that. So, but how to do that? Let us see. As I told you that there will be two torques which this compass needle will be experiencing. One is the magnetic torque which can be obtained as m cross b, or magnitude you can get mb sin theta. Theta is the angle between the magnetic moment, okay, magnetic moment and the magnetic field. Magnetic moment is actually in the direction of this, the axis of the compass needle itself, north to south, that direction. Sorry, south to north direction. This direction is dipole moment here, like this. Okay, this is the dipole moment. So now the restoring torque will try to restore the position of this compass needle, but there it will not stop. It will actually oscillate, make the compass needle oscillate back and forth around this theta angle. So if that happens, look, I can do like this. I can write this mb sin theta. So this is the restoring torque. Sorry, this is total restoring torque, which is equal to the magnetic torque. Okay, and this is how actually it will. So since this is the expression for, like, this is the expression for SHM, simple harmonic motion. So this compass needle will actually oscillate in a simple harmonic oscillation, that uh, manner. Okay, the compass needle will oscillate in simple harmonic motion. And now look, this alpha is angular acceleration. This can be written as d2 theta by dt square. d2 theta means what? This theta is the displacement, angular displacement, and double derivative of displacement will give you the acceleration. Now, if this theta angle is very, very small, then I can write this term as mb sin theta is theta. Okay, when theta is very, very small, then I can write this nearly equal to mb theta. So I have got this left hand side in terms of theta and right hand side in terms of theta. So let us see, if I equate this equation like left hand side and right hand side, what I get, I into d2 theta by dt square is equal to minus of mb theta. So this is nothing but an equation of simple harmonic oscillator. Okay, this is the restoring force representing restoring force. This is the uh, magnetic torque over here. Okay, so sorry, this is restoring torque over here. In this case, this is not force, since it is rotational motion. The rotational motion is actually produced by torque, not by force. Okay, so look, I'll just clean and then write properly. So I have got this as this d2 theta by dt square minus of mb theta. So this is acceleration. I know for simple harmonic oscillator, we know the acceleration will be actually minus omega square x. Okay, this acceleration is d2x by dt square. Obviously, this is equal to minus omega square x. If I just compare these two equations, so what I can write? See, this is a linear displacement. This is a angular displacement. So these two terms are similar. So I can just take this I in this side, then these two will be completely uh, all right to like compare from both left hand side and right hand side. So if I just compare these two, right hand side, so this x, just leave about x. You look this particular term, this mv by a, this is actually mv by I. This is actually serving the purpose of omega square. Just by comparing SHM, mechanical SHM, here SHM for the compass needle. So if I want to get this omega, then it is mv by I. Okay, m is the magnetic moment of the compass needle. It will be given, it is known. Okay, then b I have to calculate here, and I is also given. Look, so what we have got, only thing what we need is here actually this mv by I. Now time period will be 2 pi by omega, that means 2 pi into root over I by mv. Okay, this will be the time period, so which we can easily calculate from our experiment. And once we get that, if we put the value of this and this, okay, then I can find out b. So look here, I just square it out. This is equal to t. T square is equal to 4 pi square into square of this is actually I by mb. So b will be actually 4 pi square I divided by t square into m. Okay, so this will be 4 pi square. Let me just take once again. So m is here, t square. All right. So this is I by mb. Yes, all right. So this will be actually giving you the magnetic field due to, or magnetic field created by the dipole. So this is very important expression, and see there will be numerical example in your exam, or maybe a board and both, as well as board and competitive exam. You will see this kind of question. Look here, this is the thing, the whole thing I have derived over here. So this is the expression which I have derived so far. This is the expression in your book. Okay, this is 5.5 equation. So this is the expression. This is the magnetic field created by a bar magnet. So we have got we have got to learn a practical uh, or experiment, an experiment how to calculate the magnetic field, the magnitude of the magnetic field for a bar magnet, just by doing a simple experiment with compass needle. Okay. Now we'll see, if we keep a dipole in a magnetic dipole in a uh, uniform magnetic field, what happens? As I told you that if you want to rotate it by theta angle, so already what is the torque acting on this object? Now this dipole is m b sine theta. Okay, m b sine theta. Now if I just want to displace further by delta theta, okay, displace further by, I can just draw it. This is a magnetic field. Suppose you have a magnetic dipole here like this. This is the theta angle. If I just displace this by delta theta, kind of this delta theta, then how much work I have to do? That is actually, that is stored in this dipole as potential energy. So magnetic potential energy will be work done uh, by external agency to displace the dipole by an angle delta theta. Okay, so this is the magnetic dipole M. This is direction of B. So M and B, they have both, they are actually having angle in between is theta. So the torque acting on this magnetic dipole is actually mv sine theta now. Okay, and at this situation, if you want to again further displace it by delta theta. So you have to do certain work. So work done means, in case of linear motion, that is force into displacement. Okay, force into displacement. But in case of rotational motion, work done will be torque into angular displacement. Angular displacement theta. So in this case, you have to do the work delta W is equal to delta W is equal to this. Okay, this much is the work done you have to do. So if you want to know the total work done, then this is delta theta integration over there. Okay, now if the theta is 0 to theta again, and this like I'll just put it here 0 to theta mv sine theta d theta. So integration over this will be giving you a minus cos theta. So this will be mv minus mv cos of theta. Okay, so this is the magnetic potential energy. Magnetic potential energy to rotate a dipole from one angle to certain angle. So I have taken the initial angle as 0 to some angle theta. Okay, so if somebody gives you that what is the work done or what is the potential energy of a magnetic dipole if the angle between magnetic dipole and the magnetic field is 30 degree, then you have to write this m minus mv cos of 30 degree. Okay, so then you get the potential energy stored in that dipole. Okay, so this is the energy. So I have got magnetic potential energy um is minus mv cos of theta. So if I want to write in terms of dot product, I can write mv m dot b like that, minus m dot b. And see what does this say? I'll tell you. See, whenever we talk about potential energy, you have to have a reference point or reference level or reference line. Potential energy, because it is a stored energy. This is kind of a stored energy. So you need a reference from where to where you displace or you lift it, then energy is getting stored into that. Okay, so for a potential energy, you need a reference. Okay, you need a reference. So generally, reference level or reference is taken when the potential energy, where the potential energy is 0. In this case, the magnetic potential energy will be 0 if the theta angle is 90 degree. So obviously, if your magnetic field is this way and in this way your magnetic dipole, so in that case, the potential energy is 0 or work done you have to do is 0. Okay, but let us see where the minimum energy or stable state and where the unstable states are. Stable state, that means when the energy becomes minimum, look out of this expression, the minimum energy will be minus mv. Okay, when theta is 0 degree, the minimum energy state, or this is called stable state or minimum energy state. Minimum energy state or stable state. Okay, stable state is having potential energy minus m b, m into b. This is not m dot b, minus m into b. Cos theta has to be 1. Okay, so that happens when theta is 0. That means this is the minimum or stable state. So that's why any dipole you keep in a uniform magnetic field, it will try to make the angle theta as 0. That means it will always try to be oriented in the direction of magnetic field itself. Okay, it will try to align excuse me, in this direction, because in this case the theta will be 0. If theta is 0, the potential magnetic potential energy will be mv. This is the minimum potential energy you can have for a magnetic dipole if you keep in a uniform magnetic field b. And that's why, and always minimum energy states are called stable state. What they are called? Stable state. So this is the stable state most, I think we can say in your book it is written most stable state. Okay, now when theta is 0, see, this is mb sine cos of theta. So when theta is 180 degree or pi radian, then what happens to this potential energy? Magnetic potential energy will be plus of mb. So this is the maximum energy state. Maximum energy state. That means your magnetic field direction is this way, your dipole is this way. They are anti-parallel to each other. That's why the angle is phi. So anti-parallel. This case, we'll see when the dipole moment is anti-parallel to the magnetic field. This will be called as antiferromagnetic material. Okay, antiferromagnetic AFM, antiferromagnetic material. That we'll see. So this is the maximum energy state, and this maximum energy state are most unstable state. These are called energetically most unstable state. So sometimes there will be question, what is the work done you have to do? What is the work done you have to do to bring a magnetic dipole from unstable state to stable state in a uniform magnetic field? So look, there is a question in your book itself. I'll show you. You can just see that. If you just remember the expression, my potential energy is mb cos theta minus mb cos theta, then it will be very easy for you to calculate the, see here the question is this one. See this part of the question you can look at. What is the work done in moving a dipole in a uniform magnetic field from its most stable to most unstable position? What is the work done? You look, you have to do, what you have to do, most stable position is theta is equal to 0, most unstable position is theta is equal to pi. You have to take the difference of the potential energy between that two states. You look this one. So this is how you get the work done for rotating a dipole from most stable state to most unstable state. Okay, this is the work done you have to do. So work done means difference in potential energy in this case. Okay, so with this topic, like okay, yeah, so this is the thing. So that's why if you bring any magnetic dipole in a uniform magnetic field, it will try to orient in the direction of magnetic field. That is the natural tendency, because if they are parallel, magnetic moment and magnetic field are parallel to each other, then the energy of the dipole is minimum, or that is called most stable state. Now what we'll do, we'll see few comparison or analog, electrostatic analog here. I think look this, in this case just electric field is replaced by magnetic field, and electric dipole P is replaced by magnetic dipole. Every other things are all right, even potential energy and etc., which I have taught were like similar to the things which I have taught in case of electrostatics also. Only difference is, see, the E is replaced by B, P is replaced by M, and 1 by 4 pi epsilon naught is replaced by 4 mu by, sorry, mu by 4 pi. So this is one thing, and we can see the dipole. So electrostatics, in case of electrostatics, the dipole is P, and dipole moment in case of magnetism is M. Electrostatic case, the field on the axis, okay, on the C, not this is actually on the equatorial point, will be minus p by 4 pi epsilon naught r cube, and in case of magnetism also the same. For axial field, for a dipole, electric dipole, 2p by 4 pi epsilon naught r cube. This I have already derived and showed you. Look this. So in case of magnetism, it is actually mu 0 by 4 pi 2m by r cube. Okay, so every other things are all right, so equal. Okay, only few things, like if the 1 by epsilon naught is equal to mu naught. Okay, so these are the things which are analogous. Like this table will give you the analogy between electric field and magnetic field. Okay, so now we'll move on to the next topic, that is magnetism in Gauss's law. Sorry, magnetism and Gauss's law. Gauss's law, or maybe the topic can be told as Gauss's law in magnetostatics or magnetism. Look, this is the presentation I have over here. Look, we had already learned that in case of electrostatics, Gauss's law we have already learned. Just for your recap and keep a track of the knowledge, I'll just give you a small recap of that. So if you have a charged particle, okay, if you have a charged particle enclosed by a closed surface, then the flux through that closed surface is denoted by E dot A, that means ds vector. This is the area vector, was is equal to 1 by epsilon naught times charge enclosed by this closed surface. Okay, this is what we have learned in case of electrostatic. In this case also, the Gauss's law is of similar form. So first of all, what is flux? Flux is actually the magnetic field line passing through a particular area, okay, perpendicular to that area, okay, the plane of that area. So this, the number of lines, number of field lines which are penetrating or crossing this particular area, okay, this is called actually flux. And mathematically that can be in case of magnetism also, magnetic flux can be represented by this, okay, closed path integral, closed surface integral. This actually, according to magnetostatics or according to Gauss's law, in for magnetism this is 0, okay, for any case, for any closed surface you take, it is 0. We will explain why it is. So what does this say? So Gauss's law of magnetism. Gauss's law in magnetism says that closed line integral of magnetic flux, or closed line integral, okay, so mathematically it is closed surface integral of magnetic field is equal to 0. That means the flux through a closed surface, will be 0 always for magnetostatics or in case of magnetism. This is Gauss's law. So look, why? So from these two, like I have E dot n cap. So in case of electrostatics, it have E this. I have Q by 4 pi epsilon naught. Now, if I just compare these two equations, so what I can tell about this? What I can tell? I can tell that in case of magnetism, the Q equivalent magnetic charge is 0. That means there is no magnetic monopole existing in the magnetism. So B dot ds is equal to 0. B dot ds is equal to 0. What does this signify? This signifies monopole does not exist. Monopole does not exist. There may be a question. Write down the Gauss's law for magnetostatics and write down the physical significance of that. Okay. So significance is actually magnetic dipole. Sorry, monopole. Monopole does not exist for magnetism. Does not exist. Okay. Monopole does not exist. So you might be thinking, sir, what you are saying monopole and all. Monopole means suppose there is a bar magnet. You have north and south pole. If you just break them, see, they will be now two tiny magnets, but north pole and south pole will be retaining. Okay, the north pole south pole cannot be separated from each other. Okay, so that's why in case of magnetism we see the fundamental unit or source for fundamental source for B or magnetism is current loop. Okay, current loop or current loop. Okay, current loop. Current loop means what? We know current carrying loop acts as an magnetic dipole. Okay, current carrying loop again acts as a current carrying loop acts as a magnetic dipole. So look, if I have an electric dipole, I'll just now I have understood that if monopole does not exist. Monopole does not exist. That means north pole south pole cannot be separated from each other. Okay. Now see, in case of electricity, electrostatics, you have both positive and negative charge for a dipole. Okay. And if you want to calculate magnetic flux through a closed surface enclosing the dipole, so what will be the total flux? It will be actually zero. For a dipole, this will be zero. Flux will be zero for a dipole. Why? Because charge enclosed is plus q minus q. So this will be giving zero. Okay. So 0 by epsilon naught is zero. So this is how we can understand that when you have a fundamental unit for magnetism is only dipole. So there will be no monopole because north pole and south pole are monopoles. They will be cancelling each other's effect, and finally your closed surface. If you just draw like that, you have a dipole, north and south, and you have enclosed this closed surface. So the flux due to this dipole will be zero. So mathematical expression is B dot ds is equal to zero. Okay. So this also indirectly telling you that monopole does not exist because we have proved this magnetic Gauss's law. Gaussian law for magnetism that the flux total flux for a closed surface is zero, and here we are saying that for a dipole also for a closed surface dipole it is electric dipole or magnetic dipole. So the magnetic field flux contribution will be zero for that dipole because there is, in case of electric field, you see there is no net charge enclosed by this closed surface. Okay. Another point, like as I told that electric field lines are magnetic field lines are closed. Okay, but electric field lines are not closed. So magnetic field lines, suppose this is north pole, this is south pole. Magnetic field lines all the way they go like this. So this is a closed surface. Okay, sorry, closed loop. So this loop also closed loop also signifies. So closed loop also signifies that monopole does not exist. Monopole. So closed loop nature of the magnetic field line signifies that monopole does not exist. How can I prove that? Look, we can prove from here. This is for magnetic field. This is for magnetic field. This is for electric field. Look, the field lines over here, they form closed loop. Here also they form closed loop. Now, in this case, you look, these are not closed loop. Okay, starting from positive and ending at negative. Okay, in between, if some charges are there, then some of the field lines will be just deflected from this particular uh, then in that case you will not get continuous electric field lines. Okay, in case of electrostatics or electric field line case. So look, this region, if I just say this region or maybe this region, so the number of field lines entering here suppose n, the number of field lines just coming out of that is not the same. If it is m, so m not equal to n, the number of field lines entering into the south pole is not exactly equal to the magnetic field lines which are coming out from the north pole. Or in this case, this is electrostatic case, not a positive charge or negative charge. So that's why you have net flux. Okay, you have some net flux associated with uh, net flux associated with this electric dipole or electric charges, these two electric charges. And whenever you have a net flux, you have to say that you have your so your closed surface has enclosed some charge. If you have a net flux, this like from the mathematical statement, we can find out that okay, this is the thing. So if this is zero, I can say this is zero. Okay, charge. Or if the charge enclosed by this closed surface is zero, then the flux total flux also will be zero. Okay. So look here in this. I'll go another 5 minutes. Okay. So then I'll stop because I have started at 6:10. Yeah. So this is the case over here. You look. So as I said, flux will be always perpendicular to the surface you take, closed surface, perpendicular to the closed surface. At least you have to take the component of the magnetic field in that direction. That's why this is representing the perpendicular, okay, or normal direction of the surface over here. So here, if you have a see the net flux for a magnetic flux, net magnetic flux is zero for both the surfaces. Okay, so this is actually mathematical statement for continuous discrete medium or discrete matter. But if you want to get this for continuous, then you can write that integral form. Okay, so look here. So phi b is or phi b is zero. Okay, this means there is no magnetic monopole existing because your Gauss's law, states that the flux, whether it is magnetic or uh, electric flux, that should be equal to the charge enclosed by the surface. Okay. In case of magnetism, there is no monopole. That's why the charge enclosed in the right hand side will be always zero. So B dot ds, this is the flux, total flux summation over all. The total flux will be always zero for a magnetic field. Okay, so I think I'll stop it here with this part, that the difference between the Gauss's law in magnetism and electrostatic is a reflection that the isolated magnetic poles are not known to exist, and there are no sources. One more point is there is no source and sink. Source and sink means what? So in case of electrostatics, the electric field lines are starting or emanating from positive charges and ending at negative charge. So I can tell about source and sink. Source means from where it starts, and sink means where it ends. That is called, this is source and this is sink. But in case of magnetism, you have so this is sink. You have closed magnetic field lines. That's why you cannot think which one is source and which one is sink. Sink. So there is no source. Sorry, yeah, no source and no sink. Okay, in case of magnetism. So this is what it is. So I think I'll stop it here. next day actually we will start earth magnetism or earth magnetic field. So that is another important and interesting topic. We will be taking few numerical example also from that class. Okay. You people should read these examples and all. Yeah. So now what I'll tell you, I'll suggest you to ask if you have any doubt now. Okay. If you have any doubt, please ask me. Feel free to ask. Another 3 minutes or 4 minutes, you can ask me if you have any doubt.
No, sir.
So Pujita, have you understood everything? Okay. So don't have any doubt. Okay. Manjari actually has come first time. I don't know whether he has some problem. So Sargunes, the new student today. So even Nekha Venkat. So if people have any doubt for today's class or from today's discussion, whatever I have discussed so far, then if people can ask, I am ready to discuss again. If there are no doubts, then I will be ending the class today. Obviously, I will be discussing few questions after finishing the class. That time I will understand how much you people have understood. If you don't understand anything, you please feel free to ask. Anytime you can ask me, either during the class or maybe at the end of the class. Okay, so since if people don't have any doubt, I'll close this session for today. See you guys on Sunday. Okay,
Thank you,
bye.
sir.
Thank you.